Hi.
Hello.
So, can we sum up DNA replication in 10 to 15 minutes?
I think so.
Okay, so deep breath. Let's go. First of all, why does DNA replication occur?
Among so many other reasons, DNA replicates to make new cells, both somatic and germline cells.
When?
Interphase during the S phase.
Okay. So, we know that DNA, by the work of many great scientists like Watson and Crick, is a double helix.
Okay, and it's a double helix of molecules called nucleotides. We know that there are 4 different nucleotides. There are purines, which are G and A, and there are pyrimidines, C and T. What's the difference? Purines, G and A, are 2-ring structures that bond with pyrimidines. Pyrimidines are therefore 1-ring structures. Okay, so G is always with C, T is always with A. How do they bond? Hydrogen bonds. Do you want a way to remember that? Okay, pyrimidines are C and T because the words cytosine and thymine are spelled with Y's, just like pyrimidines.
So wait, you're saying that the ones that have Y's in them are called
Pyrimidines.
and the ones that don't are called
purines.
Okay, so that wasn't too bad, right? Okay, just a little refresher. DNA contains the sugar deoxyribose. Thus, the name DNA. Get it?
Woohoo.
Also, it has a phosphate backbone that holds its helical structure.
Okay, you ready to start with DNA replication?
Yes.
Okay.
I'm so ready.
We can do this. Let's go. So basically, Watson and Crick proposed that DNA replicates by somehow rupturing the hydrogen bonds. Can you show this? Okay, so they said that some reason the A and the T rupture and the bonds rupture, and that's how DNA was made. Okay, with that being said, how are we going to rupture the hydrogen bonds? Okay, so in a series of scientific experiments, it was found out that DNA replicates in what's called a semi-conservative manner. In other words, the DNA strands open up, and each side will act as a template for the other side. Okay, ready to start with 5' and 3'? Okay, so we know that it's a double helix, right? And so it therefore has 2 sides. And okay, imagine with me. We said that one strand goes from 5' to 3'. Now what about the other side? The other side, in order to bond properly, has to be anti-parallel to the other one, and therefore it will run opposite to its counterpart. So it'll go from 3' to 5'. Why is this important? We'll elaborate later on, but basically, DNA polymerase, which is an enzyme in DNA replication that you'll know more about, reads only in one direction, and therefore it will read only one strand properly.
It's kind of dumb, right?
Yeah.
Okay, so let's go. Semi-conservative replication. Unzipping the DNA strand would take too long, right? It's for this reason exactly that DNA polymerase makes replication bubbles. In essence, you get 2 forks proceeding in opposite direction to each other. This way, your DNA can form multiple DNA bubbles and therefore replicate faster at multiple replication sites. Within the turn it.
No, but this is okay.
Oh, within the replication bubble,
This
DNA
is the replication bubble.
Yeah, DNA uncoils and unzips by enzymes called helicase. Topoisomerase 1 solves a problem caused by tension generated by doing this. It opens the DNA up, and the forks begin, or at the origin of replication. Polymerase 3 reads the strands in a 3 to 5 direction,
which means it adds in the opposite direction from 5' to 3'. So it reads opposite to what it adds. Okay, so we obviously have a problem at the replication site, right? We have 2 strands, the leading and the lagging. Okay, the top one is the leading. The leading one is the one that DNA polymerase can read properly, as we mentioned before, and the lagging strand is the one that it can't read properly. So this is hard for DNA polymerase 3. So what's the solution? Okay, basically, it's not that hard. Okay, imagine with me. It begins with the adding of an RNA primer by RNA polymerase. After that, DNA can begin polymerizing. Okay, so for the leading strand, DNA polymerase 3 goes along the replication fork and it can't read the bottom strand, right? No, actually it can. And it does so by the formation of something called Okazaki fragments. And they are small portions of DNA that are going to be primed differently by RNA primer. So we have a series of Okazaki fragments, right? They're primed by RNA primer, and they need to be stuck together. So how on earth are they stuck together?
The solution?
Something called
DNA polymerase 1
comes in and removes the RNA primer, and then ligase can come and glue the fragments together.
Glue.
You know, ligate is to stick together, so enzyme ligase glues the fragments together. Basically, that's it.
That's it, really. Nothing really much happens after. Actually, what happens after DNA replication?
Does DNA undergo a process in which it edits itself?
Oh, you will have to find out next time with
Mayra
Lilly and Mayra. Lilly and Mayra. Woo.